Hey there, physics students. Welcome back to another edition of Rapid Review for Honors Physics. I want to talk today about motion that goes up and down. We're going to do kinematics, that is motion, of up and down, and I want to start with just a recap, right? You know that for constant acceleration, we use these four kinematic equations, right? Velocity, position, there's one even that requires no time at all, the no time equation as we might call it. So these are equations that we've seen before. I should take a moment to explain to you my crazy handwriting. So take a look at the lower left on this slide. If you see me writing things like X, V, A, or T, the column on the left is how I often write it. The column on the right is something I'm trying to train myself to do, but it's getting difficult to do that. So you might even see me mix it up a little bit in some of these presentations. But now you know my quirky handwriting, which comes from how I learned to write script, which was called the Palmer method. You can look that up if you're curious about handwriting history. I bet you didn't learn the Palmer method, P-A-L-M-E-R. That's how I write script. Back to this. I want you to consider the idea of a vertical coordinate system labeled y and think about, do you think this is okay to have kinematics work up and down? And spoiler alert, of course it's okay. We're going to do it a lot, right? Because it's got motion, and we're talking about motion in one dimension. We're talking about up and down motion. And there's constant acceleration, which is gravity. Well, we haven't proven or shown that gravity is constant, but hold that thought. We're going to talk about gravity in quite a bit more. So if we look at vertical motion, we have a set of four equations, and these are not new. We have seen these equations before. The only difference is I'm using the letter y in places where I would have used the letter x in the other equation. You can verify that if you'd like to check. I think that's all we need to say about justifying our vertical motion. Let's talk about gravity. I claim that gravity causes constant acceleration, and we haven't really proven that, but you could convince yourself experimentally. I'm going to take this meter stick, which is labeled we have a few key locations labeled here. I'll try to hold that vertically for the camera. And I'm going to drop this ball. Now I claim that when I drop the ball, that it's accelerating. You can check that actually. You can go advance your video frame by frame and see if the time it took to go from, I'm going to read my meter stick here, if the time it took to go from 20 to 0 was the same as the time it took to go from -20 to -40, right? Those are the same distances, but you'll find out that it's moving a lot faster as it approaches the table. You can analyze that in video. Another way you could analyze the video, looking at this picture, somebody's done a so-called multi-flash photograph. And it's kind of what you think it is. They're blinking a light on and off, and you can see the position of this dropped apple or ball, that's an apple, every once in a while, and at equal times, and you can see that it's moving faster towards the bottom. Finally, there's Vernier Video Analysis. You may have had an opportunity to use Vernier Video Analysis in your classroom, in your labs. If you have not, I highly encourage you to petition your teachers to get it and to try it out. It's really powerful, and they don't pay me to say this. You'll get to do the Apple experiment and many others and analyze the motion to your heart's content. Let's come back to gravity. Does gravity cause constant acceleration? Yeah, it does. And I don't always like you to accept my claims. I like you to test them in the lab, but for now, you'll trust me. And we will use a new letter now for acceleration due to gravity. We're going to use g. It's just traditional to use g as the acceleration due to gravity. It's just, if you see a in the equation, right, for acceleration, and it's a very special case of A. It's the gravitational acceleration. Traditionally, we use the letter G for that. And G is a vector. If we look at this, we can see that I draw the arrow above it. I will do that as a courtesy if I'm talking about vectors. If I remember to do it, I often do. That's just to remind all of us that we're talking about a vector. And because it's a vector, it has a direction. What's the direction? Well, we would call that down, right? So it's towards the center of the Earth, which, if you think about it, is kind of weird, right? Because depending on where you stand on the Earth, down is different. But if you're just standing on the Earth and you look at your little position here, standing on your local area in Westford, Massachusetts, or wherever you might be, you can consider the Earth to be a flat surface, and you can consider gravity's direction to point down, right? And so because of that, we're going to use negative 9.8 meters per second squared for gravity, right? So the negative, it just falls out of the fact that traditionally we say that that direction, that way, is negative vertically, and that direction is positive vertically. So just our arbitrary custom, good to stick with that so we can communicate with each other, but it's just an arbitrary decision that we say that's negative and that's positive in our coordinate system. Okay, so the value of gravity is negative 9.8. We'll talk more about that in a future presentation, maybe with more precision or what, but that's been measured lots and lots of times, including in our classroom. So in summary, acceleration is going to be a constant if we have gravity. The acceleration, also known as g, has a value that is known, negative 9.8 meters per second squared, and the direction is negative just because that's our coordinate system. Now, there was one little thing you might have done in a lab. You might have had a ramp in a lab. I'm going to show you a picture of something you might have done or that is typically done. And the question is, can you really do this? Is this constant acceleration? Can you use the kinematic equations? And the answer is, yep, you can. Because all you have to do is tilt your coordinate system, as I have shown here, and make it parallel to the ramp, and that's totally fine. There's constant acceleration, and all of the equations apply. You just redefine your coordinate system for your convenience, and you say that plus is parallel to the ramp and downhill. So that's totally legit, and we'll do more with ramps later in this course. Probably for now, for a while, we'll be keeping our coordinate system vertical, y, and horizontal, x. Okay? And that's all we have for now. Join me next time.